In this problem, we're going to do another head-on collision with one of the balls being stationary, but with masses that are more similar and smaller velocities. Ball 1, with a mass of 100 grams. And is traveling at 10 meters per second. Collides with ball 2, which has a mass of 300 grams and is initially at rest. What do the final velocities of the balls look like? So it could look like that, or it could look like this, 1 and 2, or it could look like this. Since the masses aren't the same, it will not be this one, because that is only true when those are the same. So if the mass is much, much greater, it'll cause it to bounce back. Like in the top case. In the middle case is if the masses are similarly sized. So I expect our answer to be somewhere between the first and the second case. Our goal is to find the final velocity of each ball if the collision is perfectly elastic. So in a perfectly elastic collision, we have PI equals PF and EI equals EF. So we need to find the total energy and the total momentum before and after for each ball, add them together, and set them equal to each other, just like the last problem. So ball 1, it has an initial velocity of 10 meters per second. So that means P1 initial is equal to 0.1 times 10 meters per second. So I just converted this to kilograms. 100 grams is 0.1 kilograms. So the initial momentum is 1 kilograms meters per second. The initial energy, so E1 initial, is 1/2 mv squared, which is 1/2 times 0.1 times 10 squared. So it's 1/2 times 0.1 times 100. So that is 50 times 0.1, which is 5 kilograms meters squared per second squared. Okay. Ball 2, just like our previous problem, has no initial momentum and no initial energy because it is not moving. So our initial momentum is equal to P1 initial plus P2 initial, which is 1 kilogram meter per second. E initial is equal to E1 initial plus E2 initial. That is 5 kilograms meters squared per second squared. So we know our initial energy and our initial momentum. So let's go to our final case. Ball 1 has an unknown velocity. The final is just going to be V1. So its momentum, P1 final, is equal to 0.1 V1. Its mass in kilograms times its velocity. Its energy, E1 final, is equal to 1/2 mv squared. Final. So that is 1/2 times 0.1 VF, well, we call it V1 squared. 0.05 V1 squared. Ball 2, VF is V2. P2F is 0.3 because its mass is 300 grams times V2. And its energy is 1/2 times 0.3 V2 squared. So that is 0.15 V2 squared. So P final is P1 final plus P2 final. That is 0.1 V1 plus 0.3 V2. E final is equal to E1 final plus E2 final. And that is 0.05 V1 squared plus 0.15 V2 squared. And now we have to use P initial equals P final, the law of conservation of momentum. P initial is 1. So 1 is equal to 0.1 V1 plus 0.3 V2. This is our first conservation law equation. And our second one is E initial equals E final. Initial energy is 5. And that is equal to 0.05 V1 squared plus 0.15 V2 squared. So again, 2 equations and 2 unknowns. I'm going to solve this first one for V1. 1 minus 0.3 V2 equals 0.1 V1. So V1 is 10 minus 3 V2. So I'm going to take that and I'm going to plug it in here. 5 is equal to 0.05 times 10 minus 3 V2 squared plus 0.15 V2 squared. 5 is equal to 0.05. Let's FOIL this out. 100 minus 60 V2 plus 3 squared is 9 V2 squared. And now we need to divide this by 0.05 or multiply it by 0.05. So this is 5 is equal to 5 minus 3 V2 plus 0.45 V2 squared plus 0.15 V2 squared. So again, these will cancel. 0 equals minus 3 V2, 0.45. Well, let's add these together. 0.45 plus 0.15 equals 0.6 V2 squared. So 3V2 equals 0.6 V2 squared. These will cancel. 3 equals 0.6 V2. So divide by 0.06. 0.06. 3 divided by 0.06 is 5 meters per second. We're then going to take this V2 and plug it back in here. So 10 minus 3 times 5 equals V1. So this is 10 minus 15. V1 minus 5 meters per second. So it is case number 1, where it goes backwards.